How long will that?
About an hour.
An hour?
Yeah.
Okay. So thank you to the organizers. This is really a great little conference, and thank you so much for Deepak for inviting me. It's going to be interesting having it on both sides. Okay, so yeah, so my talk today is about graphs and homotopy theory. So this is a bit of a weird combination. So please ask questions, interrupt me. Let's begin. So a little about me. My name is Emilio Minichiello. I got my PhD at the CUNY Graduate Center. I originally studied topology and category theory under my advisor, Mahmoud Zanalian. Now I'm an assistant professor at CUNY City Tech, and my interests have moved over a little bit to applying this kind of more abstract math to graph theory and discrete mathematics more generally. All right, so the question I like to think about is, what can topology tell us about graph theory? So topology is the study of shapes. More generally, it's the study of shapes up to continuous deformation. So for instance, I can't tell the difference between a square and a circle because I could just squash this into that, okay? So a little bit more generally, given a topological space X, we can associate to it topological invariants. So these are called the homotopy groups and the homology groups. So it's not super important for this talk that you understand what these groups are. The only thing I want you to understand is that when you have some space out there in nature, it could be extremely complicated. It could be 10,000 dimensional and could have holes of enormous amount of holes of all different kinds of dimensions. And these groups are trying to tell you something about the holes in this space, okay? And you have one for every number from 0 up, okay? And we let con of x denote the lowest k, for which pi of k, and then consequently hk, is non-zero. So you could imagine that this is 0 up to some level 5, and then the connectivity would be 5.
So yeah. Are we assuming k is bigger?
Are we assuming? No.
Okay, because like, yeah, so this theorem only kicks in after.
You're right. You're right.
Yeah, okay.
You're totally right. I'm going to have the conventions on the next slide.
Okay.
Yes. Very good point. So as you just said, there are some things you have to care about in lower dimensions. So I just have some conventions in that case. So when it's 1, we call it simply connected. Degree 0, we just call it connected. So notice that this is 0 connected, but not 1 connected. And the idea is that if I could draw a loop, so I have a torus or a donut, and I draw a little loop going around like this, there's no way for me to tighten this loop until it's a point. That's called a homotopy. But on a sphere, if I just draw a loop here, I could continuously deform it to a point like that, okay? So the sphere, the skin of the sphere is 1 connected, but this donut here is only 0 connected, okay? Now, if the space is non-empty, I call it -1 connected, even if it's a whole bunch of random pieces. And then I say every space is -2 connected, okay? These are just numerical conventions. Okay, so this is formalizing a little bit this idea I was just telling you about of continuous deformation. If I have a continuous function between spaces, I call this function a weak equivalence if it induces an isomorphism on all of the homotopy groups. So in some sense, 2 spaces are weak equivalent, or there's there's a weak equivalence between 2 spaces if I can, match up their holes in some generalized sense. So this is a picture that every topologist has to show whenever they give an introductory. I talk about topology of transforming a donut into a coffee mug. Okay, so what you see is you kind of punch down into the donut, and then you get this, but you're not punching through it, right? You're not allowed to tear it. So this is like I'm punching down, but this still has a skin here at the bottom, so there's no new hole. The only hole is this handle here. Okay. All right. So now let's switch to this point. So now the idea of topological combinatorics is I have some combinatorial object like a graph, and I want to construct a space out of it. Then study the topology of that space X using invariance. Profit, right? Learn something about the combinatorial object we started with. So that's the very ambitious goal. Does it work all the time? No, but sometimes it does. So I'm going to talk about the main theorem from a recent paper of mine that was published this year. This paper is very abstract. It's published in Applied Categorical Structures. So I'm not going to tell you a lot of the nitty-gritty details. I just want to give you a flavor of the results and why combinatorialists might be interested in. I was motivated to write this paper because I was reading about Lovasz's theorem. And I wanted to understand Lovasz's theorem through the lens of modern homotopy theory. So let me talk a little bit about Lovasz's theorem. So this is Lovasz's theorem. It says that if I have a loop graph, and I'm going to define what a loop graph is in a second, then I have this crazy sequence of symbols, right? So I have to tell you what all these symbols mean, okay? So this here is the chromatic number. I'm going to define that in the next slide. This is the topological connectivity. This is the only thing I've defined so far. The inside thing here is the clique complex of the Lovasz graph of G. Okay, I will explain all of these things, do not worry. And I hope everyone knows what that symbol is. Okay. Exactly. So let's explain what all this means. I should give the warning that this is not how Lovasz stated this theorem. Okay. Later on, another mathematician, Anton Doctorman, showed that what I just said is equivalent to what Lovasz actually said. But I'm going to talk about it in this way because it connects better to my theorem. Okay, so I have to explain the first symbol, which was chi of G. This is the chromatic number of a graph. It says, you hand me a graph and I have to play a game where I color the graph. I color every vertex of the graph in such a way that no two vertices of the same color are adjacent. So first I color these in blue, and this is fine because none of the blue vertices are adjacent in the graph. And then I color with red. And then I color with yellow. Okay, so this is a coloring of the graph, and the chromatic number is the smallest number of colors I can possibly use to color the graph. And we call that chi of G. Call that the chromatic number. Okay, so now some more rigorous definitions. To me, an undirected loop graph consists of a set V of G along with a symmetric relation. That's it. Okay. We call the elements of VG vertices. And if I have two vertices, I write x tilde y to denote that they're adjacent. So that means that between any two vertices, I'm allowed at most one edge. And if they are the same vertex, I'm allowed at most one loop. Okay. Now, as a category theory person, whenever I'm met with a new mathematical object, my immediate question is, what are the morphisms between these mathematical objects? And this is what I'm going to choose to be my morphisms. A loop graph homomorphism is a function on the sets of vertices such that if two of the vertices are adjacent, then their image under this function must be adjacent. So we see here that I'm sending the vertex A to 1, the vertex B to 2, and the vertex C to 2 as well, right? And then the edge from A to B is getting sent to the edge 1, 2. The loop on B is getting sent to the loop on 2, and AC is also getting sent to 1, 2. Okay? So this is what I'm calling a loop graph homomorphism. So you are not allowed to squish an edge unless there's a loop on the vertex.
But do you allow multiple edges or not?
No, at most one edge between every two vertices.
And maybe if you could go back to that slide and elaborate a little bit on that. So it consists of a function VF. So how does the homomorphism, what does the homomorphism have to do with the graph, the purpose of it?
Okay, so I have a function on the sets of vertices satisfying a condition, right? That condition is determined by the structure of the graphs. So I can't always map one graph into another one. Okay, I'll just skip ahead a little bit. The motivation is that a coloring G is n colorable if and only if there exists a loop graph homomorphism from G to the complete graph on N. Because what are you doing? You're mapping each vertex here to a vertex on the complete graph with N vertices, and there's no loops on the complete graph in this case. I'm calling this the unlooped complete graph. And I'm not allowed to collapse two vertices together if there's an edge between them. Does that make sense? We okay? Okay. All right. So this forms a category. So what is a category? A category is just a collection of objects and morphisms. Okay. Every object must have an identity morphism, and I have to be able to compose morphisms. So even though category theory gets a reputation for being super abstract, at least the definition of a category is pretty straightforward in my opinion. So here's some examples. The category set, whose objects are sets and morphisms are functions. Vector spaces and linear maps between them. Topological spaces and continuous functions. And the category GRL of loop graphs and loop graph homomorphisms. Okay, well, I also have a notion of morphism between categories. Okay, so a functor between categories assigns objects to objects and morphisms to morphisms in a way that preserves identity morphisms and composition. So here's a very stupid example of a functor. What does it do? Well, it's a functor from the category of loop graphs to the category of sets, right? So that means if you give me a graph, I have to give you back a set. And if you give me a loop graph homomorphism, I have to give you back a function, right? So what does this do? It takes a loop graph to its set of vertices. So I just get rid of all the edges, right? And then if you have a loop graph homomorphism, in particular, you already provided me with a function between the set of vertices. right? So this gives you a functor. Not a particularly interesting one, but you can't stop me from doing it.
So the loop graph homomorphism is also isomorphism, right?
No. Isomorphism is in a category.
No, I meant isomorphism in a graph.
Isomorphism in a graph. So for me, the definition of an isomorphism is in a category C, a morphism F from C to C prime is an isomorphism if there exists another morphism G from C prime to C such that when I compose them, I get the identity both ways.
It's bijective.
Bijective, exactly. So two graphs are isomorphic if they're the same, right? Like if they look exactly the same, maybe they just have different labels on the vertices.
So homomorphism is injective.
Homomorphism doesn't have to be anything.
It's just a map between the vertex sets, which preserves the adjacency between vertices.
Oh.
Because what I could do is I could have, here's a map of graphs, right? Just two of them get sent to the same one. But what I can't do is this. I can't map that to one point unless there's a loop. If there's a loop, then I can collapse. So you see, it's telling you something about the structure between the two graphs.
So is that a point injective or
Say again?
is that injective if you without loop?
It can be arbitrary. It doesn't having a loop graph homomorphism does not guarantee injectivity or surjectivity of the underlying function.
If you just did simple graphs, it would still be a category, right?
Yes,
But you choose loops because you want to be able to collapse edges is one thing.
exactly.
Do you care about loops in not the target graph, but the original graph? So do you want loop in a target graph so you can collapse edges? Is there any reason for having a loop in the original graph?
This is a good question. So I'm agnostic. I'm agnostic to it.
It requires you to map a loop vertex to a loop vertex, but
Exactly.
very, very useful.
Exactly. So the thing is that, I look into a textbook on graph theory and there's like 10 different definitions of graphs and there's 10 different definitions of like why people would care about them. I'm choosing this one for my particular purpose, but the category of simple graphs without loops is very interesting. And it's a terrible category, okay? If you don't allow these loops, things get very hard very quickly, okay? But yeah, so that's why I'm choosing to have loops, because then things are much simpler. Okay? But yeah, thank you.
And I just,
Yeah.
have you defined chromatic number for loop?
Yeah, it's the same definition. So if this graph has a loop, then it cannot have its chromatic number is 0.
Oh, okay.
Or infinite.
Okay, good.
Yeah, so if this has a loop, infinite chromatic number.
Good, okay.
Yeah, thank you for pointing that out. Okay. Other questions? Okay, more terminology. I say a loop graph is reflexive if every vertex has a loop. This gives me another category, the reflexive loop graphs, right? So now the morphisms are the same. I'm just restricting to a smaller class of objects. So not reflexive, reflexive. Now I get a functor. You give me a reflexive graph, I give you a loop graph by doing nothing, right? And if you have a morphism, it's already a morphism of loop graphs. Now, the interesting thing is there's a functor going the other direction. So before I could just include reflexive graphs into loop graphs. Now you give me a loop graph, I have to give you back a reflexive graph. Okay. Well, you just take the maximal reflexive subgraph. Just give you back the induced subgraph on all the vertices that have a loop on it. What happens if nothing is looped? I give you back the empty set. Right? So this also defines a functor. Okay, so that's loop graphs, reflexive graphs. I need one more object to talk about. Combinatorialists think about these simplicial complexes. So a simplicial complex is kind of like a graph, but now I'm allowed to have higher dimensional data. So if I have a set via delta, a simplicial complex on this set consists of a collection, which I call delta. So the elements of this collection are subsets of V delta, similar to closure system. And instead of those properties, though, I'm asking that if I have a subset in delta and a subset of that, then tau belongs to delta. So here we have the set 1, 2, 3, and the collection of subsets are 1, 2, 3, which I represent as dots, 1, 2, which I represent as an edge, 2, 3, and 1, 3, and then finally 1, 2, 3, which I represent as a triangle.
You're not allowing the empty set here.
It's convention. I typically do allow the empty set.
Okay, it's not listed there, I guess.
No, no.
Yeah.
I just did it for.
Okay, just make it look nice.
And then similarly here, I now have a three-dimensional tetrahedron here, which I call 1, 2, 3, 4. And then it has to have all of its subsets, which give you the triangles and the edges. And then here you see that there's two edges here, but no triangle filling it in. So in particular, every graph is a simplicial complex, right? It just doesn't have any of the higher dimensional information, any of the higher dimensional, we call these spaces and simplices, these sets here. So I might go back and forth. Now, every time I introduce an object, I'd better introduce a morphism. Okay? A morphism of simplicial complexes is a function from the set of vertices such that if I have a simplex or face and I push it over, I had better get a simplex. Okay? So here I'm sending 1 to Z, 2 to X, 3 to Y, 4 to Z, and 5 to W. And you see that what I've done is I've collapsed this here, right? So I'm just collapsing a tetrahedron onto a triangle. And that's okay because every face here is getting taken to a face there. Yeah. So now I get a new category of simplicial complexes. Okay. And I have several functors between the category of simplicial complexes and reflexive graphs. Yeah.
Actually, a question. So are you allowing for collapsing faces?
Yes. That's why I have to work with reflexive graphs.
Okay, but then you don't have to be careful about doing simplicial sets as opposed to simplicial complexes, because you might create.
We're getting there. Yeah, you're already a step ahead of me. Yes, so that's something we have to think about. Absolutely. Yeah. Okay, but we're not quite there yet. So we're still talking about graphs and simplicial complexes. And we have some functors here. So what are they? As I said, if I have a reflexive graph, you think of that as a graph with all the loops on it. Or I could think about it as a graph where I don't draw the loops and I just remember that I can squash edges, right? So if you do that, you can just think of it as a simplicial complex, right? So that's this functor iota. I just include. And then I have this functor less than or equal to 1, which is taking a simplicial complex and only remembering the vertices and the edges. And then this last one, the clique complex, I'm going to describe in more detail. It's the most interesting of these functors. It's going to take from a graph and produce a simplicial complex called its clique complex. What's it going to do? It's going to take every complete subgraph and fill it in with a simplex. Okay. But I'll explain that a little bit more. So here's the clique complex. I have a graph and I literally just every time I see a complete subgraph, I fill it in. So here's a complete subgraph, I fill it in. Here's a complete subgraph, I fill it in. Here I have a square, that's not a complete graph. So I leave it as is. So from a graph, I get a space. So summarizing, I have all of these functors.
Okay. By fill it in, you mean size 2 subsets or all the size?
Say it again?
By fill it in, you mean all size 2 subsets edges or also the size 3?
Everything,
Okay.
everything, yeah.
Go back to the previous one. So if you have a triangle, that becomes a triangle.
Mhm.
And if you have a K4, that becomes a square tetrahedron.
Exactly. Exactly. So that's the nice thing about graph theory is it's like kind of agnostic to how you think about this thing in space, right? But you can think about it as like in general positions. So like all the lines are non-intersecting like in 3 dimensions. And then you just fill it in the tetrahedron. Then you can do that for every complete graph in higher and higher dimensions.
But aren't you putting another vertex in the center?
No.
Okay, it's just the basis.
Yeah, so this is like filled in like a ball.
You have a square within that, a triangle within the square, does not matter you.
If I had put a line here, then both of these would get filled in as triangles.
No, I mean, the colored square it has another complete graph in that, the triangle.
And
Does
those
not
are all
matter.
filled in as well. Exactly.
Dashed line?
No, the other one.
The other one.
This triangle is filled in, this triangle is filled in.
So, okay, you don't use different colors.
I think that would be a little hard, yeah.
Well, you're not filling in the whole square, that could be confusing. You're not, because since you don't have a K4, you're not filling in the whole square. I think that's maybe part of your question.
Well, it's like you're imagining a tetrahedron that's filled in with paint, right?
Yeah.
On those 4.
Yeah.
vertices.
I mean, the square is filled in by virtue of it being 2 triangles glued together and the 2 triangles are.
Oh,
filled
it
in.
winds up filling all this stuff.
Yeah. So yeah. But notice that the triangle or the square rather in the middle is not at all filled in because there's no triangles to fill it in. So we're like triangulating in some sense, the thing. We're imagining embedding your graph into very high dimensional space and then triangulating.
But the set 476 is not in there, right?
476 is in there.
Oh, it does get in there.
It's one of the faces of the tetrahedron.
So like imagine a tetrahedron in 3-dimensional space, you rotate it around, it has these triangles on it every side. So it's just a little hard to draw it, but like they're all filled in. Yeah, thank you. So this is the summary. I have now defined all of these things. This is inclusion, maximal reflexive subgraph, taking the vertices and edges, and the clique complex. All right, one more construction. I'm sorry, there's a lot of definitions we have to get through. Yeah.
So if you have the K4 was a 3-dimensional object.
That's right.
But K5 would be a 4-dimensional
That's right.
object, so you can't draw it.
Exactly.
Yeah.
Exactly.
Thank you.
Drives a Schlegel.
Yeah. you can draw it in many different ways. Yeah.
Rapid projection.
Okay. Now, this construction is not super important that you understand it. I just want you to know that it exists. If I have 2 loop graphs, I can get another loop graph. So I call it H upper G. This is called the exponential graph. Okay. The vertices are functions satisfying a certain property. Okay. I really don't want to dwell on it because it's a little bit complicated. It takes a little bit of time to absorb, but it's not super important for what we're going to say. I just want you to know that this is something that happens in category theory a lot, where you have 2 objects and you can come up with another object such that this property holds. So if I have H and G, I can cook up this new graph. And if I map into it by another graph, that's the same thing as taking the product. So in sets, what this would be is I have a set A and I have a set B. And then B, A is the set of functions from A to B. Right? So if I map into a set of functions, I could take this over and map from the product. Okay. So this is called the internal Hom construction in loop graphs. All right, so now we have all the tools to describe the Lovasz graph. So what is it? I take a graph G, I raise it to K2. What is K2? It's a complete graph on two vertices, which is the same thing as just an edge, right? So I take my graph, I raise it to an edge, and then I take the maximal reflexive subgraph. So I want to make sure everything's looped, okay? So here's what it looks like when G is a 4 cycle. Okay, so I want to try and give you a little bit of intuition about what this thing looks like. You imagine that you're sitting here at this vertex 1 and you're looking out at all of your adjacent neighbors. And for every adjacent neighbor, you put a vertex above it. Okay. Then I do that at every vertex. So here I'm looking out from 1 and I see 2. So I go 1, 2. So these are like directed edges now. I'm at 1, I look at 3. Here I'm at 3, I'm looking at 1, so I get 3, 1. 3, looking at 4, I get 3, 4, and so on. Now, when are these things adjacent? They're adjacent if, when I look at the opposite vertex, they're adjacent. So 1, 3 is adjacent to 1, 2, because 3 is adjacent to 1, and 1 is adjacent to 2. Now, 1, 3 is not adjacent to 2, 4, because 1 is not adjacent to 4, and 3 is not adjacent to 2. Okay, so it's kind of this funny trick where you're like looking at the different ones. But this gives you the Lovasz graph.
And both of those have to be true for
Both of those have to be true. Yeah, it's not enough for one of them to be true. You have to look at both of the opposite vertices. And what you should think of this as is a kind of relationship between the edges. But there's a direction here. So you imagine it as directed, and you want to know what kind, like there's some kind of relationship between this directed edge and this directed edge. Okay. So what does this look like? So what is this? I have C4 sitting here. The Lovasz graph is 2 copies of K4. Okay. But they're disjoint. So I just have 2 copies of K4 kind of floating there. But 2 copies of K4 is not connected. Okay. So this thing is disconnected, which using my annoying conventions from before means it's -1. Its connectivity is -1. So this gives me a lower bound by Lovasz's theorem of the cycle, the 4 cycle. So the chromatic number of the 4 cycle has to be greater than or equal to 2. And in fact, this is a sharp lower bound. It is equal to 2. I can 2 color a square, right? Okay, so this is kind of an intro. So I was learning about all of this, and I wanted to know if the following was true. So I take 2 graphs, and I do this thing. I get a new graph, and I take the clique complex of that. And I wanted to know if that's the same thing as the internal Hom in spaces. So I could take 2 spaces, and I can do this exponential construction, which gives me this thing. So this is a space of continuous functions between the spaces. Now, there's a sense in which you can immediately verify this is not true, but I was wondering if there was a less naive sense in which it was true. So there's something you can do on categories, which is called putting a model structure on it. And if you put a model structure on a category, for every 2 objects in that category, you can cook up a space called R-Hom. And so I wanted to know if there existed a model structure such that this space was weak equivalent to this one. And there's a little typo here. This should have maximal reflexive subgraph. So this was the start of my investigation into this. This just repeats what I was saying. So homotopy theorists use model categories everywhere. They use it to organize different categories that they're interested in. So two categories that homotopy theorists like is the category of topological spaces. But topological spaces get really, really complicated really quickly, and you have to do all this really annoying point set topology that people don't like and don't want to think about. So what they do is they use something else. They use something called simplicial sets. Okay. So simplicial sets are a discrete combinatorial model of topological spaces up to homotopy. And this is this funny thing where I learned about simplicial sets way before I learned about simplicial complexes. So in the homotopy theory world, simplicial sets are the supreme kind of approximation to spaces. But in the combinatorial world, simplicial complexes are the kind of normal approximation. And there's very little overlap in the literature between the two, which I thought was strange. But in any case, simplicial sets are far more complicated than simplicial complexes. In a simplicial set, you also have this idea of having these triangles and tetrahedra and stuff, but now I can do all kinds of crazy stuff and glue them together however I want. So in particular, I can have a loop. I can have a vertex and I can have a loop. You can't do that in a simplicial complex. You need multiple vertices, right? I also have directed edges. Everything is directed now. And furthermore, I can have something like this, like a pillow, right? So I can have where like the vertices are the same, but the edges aren't, and it's a different two cell, okay? So the point here is that simplicial sets are very different than simplicial complexes, even though they both have the word simplicial. Okay, so I found out that Matsushita had constructed a model structure on loop graphs in 2016. So what did he do? He constructed a functor from loop graphs to simplicial sets. So remember, simplicial sets are like complicated simplicial complexes that homotopy theorists really like. So if you give Matsushita a loop graph, he'll give you back a simplicial set. Okay, so what is it? So I take a graph, G, and I want to produce a set of simplices. So, you know, you have a point, you have an edge, you have a triangle, tetrahedron, and so on. And I have a set of all of those. So in degree n, I have to produce a set. The set of n simplices in the simplicial set is the set of maps from a complete graph into your graph G. So in degree 0, this is the set of vertices because K0 or K1, sorry. Yeah, you probably want n minus 1. So you map in vertices, then you map in edges, then you map in triangles, then you map in K4, K5, and so on. And every time you're filling it in. Now this is much bigger than the clique complex because every time I map in an edge, I can also flip it and map that in. So for every edge, I get 2 maps. For every triangle, I get 3 maps. I get 3 factorial maps, 6 maps, right? Because I can take a triangle and then it has S3 worth of automorphisms. So this thing is huge for any graph. This is a massive space you can cook up. But it turns out that it's weak equivalent to the clique complex, which is very small. Then, through this construction, Matsushita transfers the homotopy theory from simplicial sets to loop graphs. To do this, he has to do something kind of subtle, where you have to subdivide the simplicial set twice and then transfer it over. So this is kind of a weird thing, and I want to just briefly say why you have to think about it. So one thing that's really nice in topology and homotopy theory is when you map one space, you think of one space as a subset of another one, and you want there to be, and you think about the neighborhood. So I have a big space, X, and I have a smaller space, Y, and I want to think about a neighborhood of Y in X. And it would be really great if this neighborhood was weak equivalent to Y. If I could take the neighborhood and collapse it down to Y. It's a little hard to see why this is so desirable, but it's very, very nice to have. Makes life a lot easier. Well, in the realm of simplicial complexes, doesn't get satisfied very often, right? So here I have a simplicial complex L, and I have a simplicial complex K sitting inside of it. And if I took the neighborhood of this thing, if I took all the edges and all the vertices that are distance 1 away, I would just get the whole thing. Now this can't collapse onto this, right? Because this has a hole in it, but this one doesn't. So it's not that whenever this property is satisfied, we call it an NDR pair, neighborhood deformation retrap. So this is not an NDR pair. But an incredible fact that apparently has been known forever, but nobody ever really says it in this way, is that if you take a simplicial complex, you look at a subcomplex, and you subdivide both of them twice, this is always an NDR pair. So you can see it in this example. Now I have this subcomplex sitting inside of this one, and I take the neighborhood. Well, the neighborhood is just these two dangly edges here, and not this guy. This can be collapsed onto this. I just take this and push it like that, right? And you can see also that if I only done it once, it would just be a point here and not these guys, and the whole thing would again be the triangle. So you really do need 2 subdivisions. Okay, so now my theorem is that what Matsushita did was he actually went like this with his construction, and I figured that you could factor his construction through a whole bunch of pieces. So I broke his big ass construction down, sorry. His big construction down into pieces. And I showed that you could transfer the homotopy theory to here, and to there individually. And then furthermore, all of the homotopy theories are equivalent. There's also one other thing I proved, which is a technical thing, that all of these model categories are proper. So I'm not going to say what that means, but I'll tell you what a consequence of that is. Let's just skip this. So yeah, so this was false, but this corollary I find interesting. So in topology, there's something called the Meyer-Vittoris sequence, which tells you how you can get the homology of a space by chopping it up into pieces. So if I have a space X that can be written as a union of 2 other spaces, then this tells you how to compute the homology in terms of the pieces and the intersection. Okay? This is something that topologists really like, and it would be really great if this was compatible with the clique complex. So suppose I have 2 graphs and I glue them together. Right? So this is what that looks like. And then I take the clique complexes. Now I have spaces. So you see in the first 2, clique of H and clique of K, they have holes. But clique of H union K does not have a hole. So when I run through this exact sequence of groups, of abelian groups, I get this. But this is not an exact sequence. If it was, then Z would be isomorphic to Z squared. It's not exact. If you subdivide twice, if you take the clique complex and you subdivide twice, and then you glue, then it is exact. So there's something really weird going on where you can approximate a space using graphs by taking the clique complex, subdividing twice, taking the one skeleton, and then this thing retains all the information of the space of the clique complex, and you can work with it combinatorially. Matt?
So you got this by taking a graph and then thinking of it as a simplicial complex.
I take the clique complex on both of them.
Oh, take the clique complex, right? Subdivide twice.
Then
and
take the one skeleton.
And then, yeah, just take the,
Now glue them together
okay,
as graphs.
gotcha.
So that's the main part of the theorem. So in summary, Lovasz showed us that topology can inform combinatorics. Matsushita showed there's a model structure on loop graphs. I extended his construction to simplicial complexes and reflexive graphs. And I also showed that the model categories are proper, which gives us a way of repairing Meyer-Vietoris for graphs. So I have a bunch of questions about this. Can I extend this to other ways of obtaining spaces from graphs? Because this is a whole industry now. There's ways of thinking of mapping cubes into a graph. Also path homology. How can I compute arbitrary homotopy colimits? And what other constructions play well with the clique complex? I don't know the answer to any of these. So that's it. Thank you for your patience. Any questions? Deepak?
No, go ahead.
No, you.
This somehow connects to Lovash's proof about the Kneser graph.
So I used Kneser's theorem. I'm sorry, Lovash's theorem inspired my theorem.
Right. Okay.
Because I understood this connection with the clique complex and the chromatic number, and then that made me think about because what he does is he takes graph upper K2 and takes clique complex of that. So then I wondered, what about any graph instead of K2? And then that kind of inspired that. So it's not directly relevant, but it's motivating, and I got to introduce all the functors using it. Also, Lovasz didn't write it like that. He had a completely different construction, but it's equivalent.
What was Lovash's motivation?
Lovash's
Just a
motivation
rule for chromatic
is there was something called the Kneser conjecture. So there's a class of graphs called the Kneser graphs, and there is a upper bound on the colorings of Kneser graphs that's very easy to obtain. And he wanted a lower bound so he could figure out what the chromatic number of these Kneser graphs was. And he proved it by proving that theorem. But instead of using this kind of category theory language, he just said, take a graph, cook up what's called its neighborhood complex. So now you have the same set of vertices as the graph, and you connect two of them if their neighborhoods share a point. And then if you have a triangle when all three of their neighborhoods share a point, and so on. And this gives you simplicial complexes, and then he used that.
But he didn't say in simplicial complex, he just spoke like that.
No, he said a simplicial
Oh,
complex.
he did, okay.
Yeah.
And did he use topology
Yes.
stuff to do? Okay.
Yes, yes, exactly. So the point is that the idea is this: if I have, if there is a certain coloring for a graph, then I have this. Lovasz computed that his neighborhood complex, and then some other ones that are equivalent, for this is a sphere. This is a sphere, and it has a Z2 action on it. Now, if I had such a map like this, I would get a map from the space, the Lovasz space here, to a sphere. And if that thing had a map from a sphere into it, then I would get a map from a sphere to a sphere, right? And then there's something called the Borsuk-Ulam theorem in topology, which says you cannot have a map. There exists a Borsuk-Ulam says that if I have a continuous function between two spheres, that's Z2 equivariant that reflects the antipodal map, then M has to be greater than N. Is that right? Where M is less than, right? It's one of those. Anyway, the point is that
The circle will embed into the sphere as the equator.
exactly,
So,
yeah. So if I had such a coloring, then I would get, and if the thing was connected, then I would get a map from a sphere into that to a sphere, and that would contradict the Borsuk-Ulam theorem. That's what Lovasz proved. That's what he used. That was his argument.
One of the original hopes was you to go to topology and use that to go back to graph theory. I guess Lovasz managed to do that.
He did
I
that.
did that. Do you have hopes? I mean, you didn't do that.
My hopes were dashed, unfortunately.
But do you have some hope that you can go back, take, I mean, interesting stuff into topology? and go
Absolutely,
back?
yes.
Is there some sort of target
There's
theorem
so
possible you have in combinatorics?
so I don't have so it's kind of a hard question to answer because right now there's so many attempts at doing this. There's so many different ways of doing this. This is one way of thinking about this, of getting a space from a graph that like it's very underexplored. So there's still like it's more exploratory at this stage. So we know this theorem. We also know that if you take the Michelskian of the graph and you do this Lovasz construction, that's the suspension in topology. So you're seeing this weird sort of connection between graph theory and topology here. And there's a bunch of other results that kind of tie into it. But what my theorem is saying is that, you know, graphs are good enough for all spaces. So this gives you a way of producing graphs with certain properties. But yeah, it's not quite there yet where you would be like, oh, I could apply this to a combinatorial problem. But right now, just understanding these connections and these hints is kind of my goal, at least at this point.
Can you go back to the very beginning where you define the negative connectivity? I just want to make sure what I understand what you.
Everything is -2. Remember that one?
Yeah.
I like that.
Okay.
Yeah, it's very strange.
So what do you mean -1 connected?
If the only space that's -2 connected, but not -1 connected is the empty set.
-1 connected, it just means you're a space.
Just means you're non-empty.
Or, yes.
It just, okay.
But the Lovasz space can be empty, so that comes up.
And then if you're n connected, then if you're everything less than that connected.
So finding bounds for chromatic number is generally a useful thing to do.
Yeah.
So is there like a cottage industry of people using Lovash's Lovasz graph to get a bound? on the-
Absolutely. Yeah, so
This
this,
for different kinds of families and
Yeah.
stuff.
yeah. So stretching my knowledge a little bit, but there's a class of Schreiber graphs, I think, stable Kneser graphs. They extended these results to hypergraphs. There is a whole cottage industry of coming up with of lower bounds on the chromatic number using topology.
And constructing Lovasz graph.
Exactly. Yeah.
This cottage industry, do they also, you did a lot of category theory.
Yeah.
I guess to break up, to have functors between different categories. Is that more unique to you or is that?
Yes. Yeah. So topological combinatorics is like a kind of branch, right?
Yeah.
But category theory has not really touched that branch yet.
And your use of category theory seemed like was to go between different spaces,
Different categories.
different categories. Yeah.
I mean, some people in the field know category theory and use the language and stuff. Matsushita really, used category theory, but it's not super prevalent.
I was curious, is there a connection to the matroids? Because
Yes.
I saw that at some point you were introducing directed graphs, and I know that the connection there is with oriented matroids. So
Yeah, so I shouldn't have said yes. I was just excited when you said Metroid. Because what can I say? To Metroids, you can ask a lot of the same questions, right? But as far as I know, I don't know if people have done this kind of construction on just like general Metroids. As I said, like there's lots of you have this big result and then people like trying to apply it in different ways. I haven't seen specifically like a Metroid version of it. Yeah.
Like, is there a way to get a space from a matroid the way you have?
I mean, that's what Junaha got like the Fields Medal for.
Oh, really?
Right.
Okay. Yikes.
But I mean, I'm being facetious a little bit, like, he comes up with like cohomology theories and then works with that.
But matroids don't have vertices, and this is
Yeah.
much based on vertices,
Yeah.
right?
Yeah, so maybe that's why there is no sort of connection
It's
there.
a way of extending the matroids. I should have asked you a question.
Right, I was gonna say, Ed, are you allowed to ask?
I'm stepping on your toes.
Yeah.
Yeah.
I just want to understand a little better what your theorem says. So it's like you have loop graphs and then in terms of homotopy theory, these are equivalent to spaces. Like you can turn a loop graph into a space and vice versa. And if the spaces you get from two loop graphs are homotopy equivalent, then that induces a notion of equivalence on the loop graphs. Can you say more about the notion of equivalence that you get between two loop graphs?
Oh, you
To
want like a
homotopy?
combinatorial way of
Yeah.
understanding? I have no idea.
Okay.
Yeah, that's a super
Okay, it's hard, right?
Super hard.
Okay.
Yeah. When do like two graphs, like if I have maps between them, does that give me the same space up to weak equivalence? Yeah, I have no idea. Yeah. Yeah, it's interesting because I mean, like, that's as hard as asking about like weak equivalence of spaces. But like here you do have like kind of finiteness, but
I mean, what about
It's-
like
it's-
homotopy equivalence?
yeah, it's interesting. Yeah. Yeah.
Anyway, I'll bother you about it.
Yeah.
Yes, speaker again. Okay, so I guess we're going to lunch break now?
So we have one poster,
Okay.
Two.
but two, yeah. Good.
This was a lunch or poster stuff.
What should we do the
So after
posters?
lunch, we go back here.
Nice. Maybe.
Are we gonna set them up?
Or we could have posters now.